One person who has done a lot of work in this area and who has been the inspiration for me and many others in the field is Oisin Mac Aodha from University of Edinburgh. He's a reader, similar to associate professor in the United States. He made a keynote last year on the Tackling Climate Change with AI workshop at ICLR in Vienna, and showed all these amazing things that you can learn using relatively simple approaches and with very limited supervision and very limited annotations. How merely a sparse species observations, when combined in large numbers, can make a model learn geographical properties of the world. He did his PhD at UCL and then a postdoc at Caltech with Pietro Pirona. He has published papers on AI for conservation and biodiversity monitoring, 3D understanding, human-in-the-loop machine learning and interpretability, self-supervised and representation learning, fine-grained visual categorization. We're really happy to have you here today. Please give a hand to Oisin.
Good morning, everyone. It's nice to see so many people here. Is this okay? You can hear me? Good? Great. Yeah, so thank you again to the organizers for inviting me. It's a really exciting event, and I'm really very thrilled to be part of it today. So I'm going to talk about some work that we've been doing in my group, but also along with collaborators, as you can see on the title, on the topic of species distribution modeling. Let's have a look. Okay, so just to give a bit of a backstory, I'll rewind the clock a bit to kind of give you a sense of how we got into this problem in the first place. I'm guessing many people here have heard of iNaturalist. Yeah, great. So iNaturalist is this citizen science endeavor, this platform where members of the public take photographs. Also, they can record audio of nature, and they upload it, and they help each other identify what's present on the platform. So, for example, up until recently, there's on the order of around 250 million different observations. So, an observation is a recording in space and time of a specific taxonomic entity, like a species. So, for example, you can see here that iNaturalist has about 500,000 different species data from that many on the platform, and that's observed by this kind of amazing network of 3.5 million people distributed all around the planet. So this is this really cool distributed volunteer effort to kind of record biodiversity around the planet. And what's really impressive about this platform is it's not kind of focused on one taxonomic entity, it's just our group. It's really diverse in terms of what people upload. And so we have this amazing collection of images of mammals, plants, birds, you name it, it's on the platform. So we started working with iNaturalist, I guess, over 5 years ago at this stage, bit longer than that, on this classic question of what is in an image, this computer vision problem. So given some image I, what species Y is present in it? If you recall from a slide a few minutes ago, this is tough because that possible set of labels is on the order of hundreds of thousands of entities. It's pretty clear, though, that if you take a task like this to a human expert, this is not how they're going to answer the problem. They're going to want to know, well, where did you take the photograph? And this is a pretty crucial piece of information because it's going to help you disambiguate potentially confusing pairs of species. You might have two species that look quite similar, but they're found fundamentally in different locations, and thus it's a pretty crucial piece of knowledge to have. We can kind of factorize this out. So instead of saying what species is present in image I at location X, we can kind of separate that out into two different parts. And we know how to do the first part. This is a standard image classifier. You could train some CNN or visual transformer to actually give you some distribution over the possible sets of classes. This next part, though, wasn't so clear to us, or certainly not when we started this project a few years ago. So this is some kind of concept of a geographical prior. So given a location X, what species are likely to be present at that location? And what we really want is some kind of representation of the range of a species, so the set of areas where this thing is likely to occur. And so this is an example from the IUCN, or BirdLife International, and it is a a depiction of the range of this house wren. So pink areas are the areas where the species is said to be found across the year. In practice, the observations that you get on platforms like iNaturalist are highly spatially biased. So we have a lot of data kind of in North America in this example, Central America, but we have huge data gaps in the middle of South America. And so this is obviously problematic. What is striking is that we have a pretty limited understanding of where most species actually occur on the planet. We have all this amazing rich observation data, but it's sparse. And so for, the order of maybe 10 million or so species that are described by science, 2 million that are described by science, only about 100K of those actually have reliable range maps. So it's a pretty small fraction of all possible species. And this is a problem because these range maps, they inform conservation priorities. There's next level problems, understanding how those ranges are changing over time. So this is like a pretty crucial, basic, factual piece of information that we would like to have, but it's currently missing. And so, if there is a good side to all of this, one of the good sides is that we're seeing this amazing explosion in biodiversity observation data being collected, and actually primarily being collected by members of the public. So you can see here, at the start of this year, GBIF, which is kind of an aggregator for lots of different platforms, lots of different data sources, they just hit this 3 billion milestone. So 3 billion observations of natural objects. Okay, so the core task or the core objective today is to talk about the work we've been doing on developing species distribution models. There's a huge and really rich history on this task, and obviously I won't be able to cover it in any kind of meaningful detail today, but this goes back to early work even in machine learning. So many people might have heard of Max Ent, a paper from ICML from a few years ago. There's also really interesting work on building hierarchical Bayesian or probabilistic models where you can encode very problem-specific information into those models, so things about relationships between entities and so on. Recently, we've seen this rise in deep learning solutions, and they offer this, alternative sets of benefits. We can start doing things at a scale that wasn't possible with previous models. We can use modern techniques for training these models, and we can also incorporate additional information like remote sensing imagery or climate observations in a much more seamless manner into these models. If people haven't seen this is actually a really cool review paper. It's kind of targeted for an AI computer science audience, and it gives an overview of this problem. So I'm not part of this project, but I think it's definitely a really cool paper to check out if you've got interest in this. Okay, so the task is, can we train a model that can estimate the probability that a species is present at a location of interest? But what we're going to have is this highly biased and sparse data set where we have only presence observations and no confirmed absences. And I'll explain what that means now. Okay, so the ideal setting would be to have, for example, for a given species, we'd have a dense set of observations where, in this case here, green indicates a location where the species is determined to be present, so someone's gone out and found it, and red indicates locations where someone has gone to that location, spent a sufficient amount of time, and determined that the species is not present at that location. So you could think of this as kind of a simplified map of the world, for example. In practice, what we have is this presence-only setting. So we only have observations of where something has been observed, and we don't really have any confirmation of where something is determined to be absent. Okay, so let's continue this kind of toy illustration. So here we have data for 3 different species. We've got a green, a blue, and a red. The way that the kind of models that we're developing work is we can kind of decompose them into 2 main parts. So one of them is a location encoder. So think of this as some kind of encoding or representation of physical space. So this is a multi-layer perceptron or a neural network that's conditioned on a location X. Given that location X, it's going to transform that into some high-dimensional representation. And the idea being that that representation should characterize somehow that physical location, so that when in the next step we're going to learn representations for species, there's some idea that affinities between location and species represent the likelihood that something is present there or not. So in some sense, while I haven't changed the framing of the problem from traditionally how people think of this, I think it is quite interesting to think of this in the lens of a representation learning problem, where we're trying to learn representations of locations and representations of species. Okay, so this is our location embedding. This is some, again, d-dimensional vector. Separately, we're going to learn a representation for species. So each species, in this case we've just got 3. You could think of this again as some kind of vector for each of them. And so the inner product between a location encoding and a species encoding, transformed by some nonlinearity like a sigmoid, gives us a probability of whether that species is present or not. So this is essentially a multi-label learning problem where for a given location we have a set of possible species that are present there or not, and we're trying to produce high values when they're present and low values when they're not. And so in the course of training, we're going to train this location encoder and we're going to train these species embeddings as well. And by the way, definitely stop me if there's any questions along the way. I'm happy to clarify anything. Yeah, Dan. The flame, yes, the flame means that it's being trained. Yeah, so we're going to train these things. Nothing's on fire. You don't need to worry. Okay, and so good question though. So the result of this is that we can then query an arbitrary location x, and we get a continuous value between 0 and 1 for a given species. But actually, in practice, we can also get a value for all possible species of interest for that location as well. And if you go back to this motivation from the start of developing this geographical prior, this is now a really compact way of evaluating a given location to determine what species are likely to be present there or not. Okay, so we had a paper about 2 years ago at this stage at ICML introducing this framework, and I don't have time, unfortunately, today to go into a lot of the details of how we train it, because there's a lot of kind of nuance with respect to how you actually deal with the fact we have no absence information. But I'm going to have to gloss over that today. But what we were able to do in that paper is we were able to take this very simple framework and we were able to use it to train models for 50,000 different species on the orders of tens of millions of observations. And the actual resulting model that comes out of this is this really compact, small entity on the order of like 100 megabytes or so that you could actually then deploy, for example, on a phone in the context of these iNaturalist type use cases and use it as a prior for estimating the range of a species. And so to give you a kind of a flavor, maybe instead of going into the details of how we train it, I want to give some insight into what these models actually learn. So if we train this model on a very small number of observations, so this is a relatively small fraction of the total data, just 10 observations per species, you can see that here, this is basically a visualization of these location encodings, this d-dimensional feature vector. So I just project this high dimensional vector down to 3D and visualize it. So we have this kind of coarse representation of space where it's separated out broadly continents from each other, but there's no real kind of like meaningful detail in this visualization. If we increase the number of observations, so I increase it here to 1,000 instead of 10, nothing's changed about the model, it's just the data that it's trained on. We get this kind of interesting emerging property where we can see kind of geographical structures like maybe the Sierra Mountains here, the Alps and so on, actually emerging from this model. So this is a model that's not trained with any ecological or climate variables as input. It's just trained purely on species observations. But because of the structure that's inherent in those observations, the model has to learn a representation that satisfies the fact that certain species appear in some locations and certain ones appear in others. You get this emergent property where we get this kind of underlying structure or representation of the Earth coming from it. Okay, so we can also look at these representations of species as well that are encoded inside the model. So remember, these were these vectors where we learn a vector for each of the species. In this case here, we have 50,000 species. So this here is just a kind of a TS&E plot, or again, another low-dimensional plot of the species that are represented by the model. So you could think of in this toy illustration, we've got a green species, a red one, and a blue one. These are just different locations in this embedding. But in practice, each of these points in this space, when multiplied by the location embedding for all locations, results in a range map. Okay, so this is the kind of like the inner product that we talked about before. We get a score for each location, whether something is present or not. So you can see in this example, it happens to be on the east coast of Australia. Now we can see here, we can walk around this space. So what's happening is I'm just kind of visualizing different species. And what should be hopefully apparent is that locations that are, not locations, but species encodings that are similar manifest a similar range predictions for those species. So in a sense, the model has learned to kind of represent species such that similar species in the species embedding space will manifest as similar range predictions. And again, this is kind of, maybe hopefully kind of intuitive, that this is just what the model needs to do to be able to kind of represent this complex structure. But it also goes to the heart of the kind of benefits of learning these joint models, that we're actually sharing information across species. And so when we have these data poor species versus data rich ones, the model is able to kind of use the knowledge it has about other species to fill in these data gaps. Okay, and then just to kind of again quickly visualize what this looks like. So we get these in general relatively spatially coarse but kind of useful range maps. Here's the observations from my naturalist, and see here the prediction from the model. Again, another species here, and here's one from New Zealand, etc. Okay, so it was important for us when we were working on this project to think of a kind of a quantitative evaluation framework for this problem, because I think this is one of the challenges that was preventing AI machine learning researchers from actually making progress. That would, while the data was out there for training models, it wasn't really clear how they could actually evaluate success without having, an expert collaborator and potentially experts in all these diverse taxonomic groups, which is not really scalable or feasible. So as part of that work, we wanted to put together a kind of a first attempt at a quantitative benchmark for this problem. I mean, first in the sense that first for the machine learning audience. Obviously, there's been a lot of work on evaluating SDMs from the ecological statistics side for many years. So we have these different tasks, so estimating ranges, for example, of bird species or other varied taxonomic groups, where we've curated kind of best-in-class expert range maps for this problem. So you could think of the task then being, how close is my prediction to the expert map? And then we've also got this geographical prior or image classification task that I motivate the problem with at the start. So this is a kind of another task that we can evaluate performance on. Great. Okay, so looking at performance here on the range estimation problem, here each dot is a different model trained on different amounts of data. So I talked about models having like limited data versus more data. So, one perhaps not too surprising observation is that the more data we give the model, the better the performance. So here we're measuring the agreement between the predicted range maps and the expert one with using mean average precision. But what's quite cool is if we increase the number of species, so here I'm increasing data per species on the going upwards, but I can increase the total number of training species as well. The test set always stays the same in this case, so I'm not changing the test set, I'm just either increasing data per species or I'm increasing the number of them. And what we also see is that performance improves. So this is kind of quantitatively verifying this observation that I can take data from more species and that will even help other additional species. And so this is quite a cool, I think, outcome of being, again, able to train these models on many species at once. And again, looking at this kind of visually, we can see here with the limited amount of observations, we get these higher number of false positives, which are shown in green. And as we increase the number of training examples for species, we see a reduction in these false positives as well. Okay, and not to belabor it too much, we can then quantify performance against, this is just one simple baseline, but there's an extensive evaluation performed in the paper. Okay, so a naturalist deployed a variant of these models, I guess 2 years ago or 1.5 years ago at this stage. And the primary use case was to assist with computer vision predictions. And what we're seeing here is a breakdown of performance of their computer vision classifier across different taxonomic groups. But actually, it's kind of just mainly important to look at the average column here. So these are just two different versions of their models, but without using any geographical information, the models are getting kind of 80% classification performance. And the thing I think that's kind of, for me anyway, was mind-blowing to remind myself was that this is 100,000 way classification. So for a given image, there's 100,000 different species that their vision models are trained on. And so we're getting around 80% performance just using the classifier, pretty vanilla off-the-shelf image classifier. but dropping in the geographical prior, or combining the two together, we're seeing a 10% improvement in top one accuracy, which I think people that have worked in vision have an appreciation of how like even 1% is like a CVPR paper's worth of improvement. So getting 10% from doing something relatively quite simple is a really nice, I think, outcome of this. Okay, they're also using these kind of models to do things like anomaly detection. So here's an example of this spider. I think that's primarily found in Asia and has been recently observed in Massachusetts. So finding things that are outside of their typical distribution is something that's important to flag to the community. Oh, I'm also, sorry Olaf, I'm getting more. Perfect, okay, thank you. And so recently, actually just at the start of this year, we released a data product, which is a computed range maps for a whole bunch of different species, again, 100,000 species. And I think, you know, while this is certainly not perfect by any means at the start, I think it's kind of a starting point for us to then think about how we can improve these further, and we can and generate ultimately better range maps for the community. Okay, so that is the kind of like the background setup in some sense. So what I want to talk about for the second half of my talk is some of the more recent work we've been doing about how to incorporate additional information into these models. Yeah. Yeah, good question. So question is about resolution. So in practice, there is no explicit resolution in the model in terms of training it, because it's just taking coordinates as input. So it's kind of this continuous or implicit representation of space. In practice, when we evaluate, we do discretize the data for the evaluation data, and we just evaluate the model by querying the center of a set of kind of tiles on Earth. And I think I'd have to look that up. We're using this H3 geospatial library, and we're using a kind of resolution 5, and I can't remember what those cells relate to, but it's kind of maybe a couple of 100 kilometers squared kind of regions. But yeah, the takeaway is like the data kind of drives the resolution in terms of training, and the more like detail in some sense, or more data you have locally with a model with sufficient capacity, it should be able to kind of learn those transitions. Yep. Yeah, I mean, I guess it's a good question. Can we predict invasive species? So in a sense, what we're doing is we're capturing the distribution of data on iNaturalist with all its, you know, imperfections and all its positive attributes. So I guess you could start doing things like the anomaly detection I talked about, which is finding things out of range. So I guess that maybe is the closest thing that we've looked at to that at the moment. But you know, there's clearly a lot more that could be done there. Okay, so we have all these amazing advances in large language models. I think Olaf even kind of alluded to this at the start of his introduction. There's a question here of like how much ecological knowledge that these models actually contain, and would this be some kind of useful supervision that we could incorporate into the distribution models that we're developing? And so Philip, who is here today, has a poster on exactly this question: how do we assess the knowledge contained in these models? The kind of takeaway is there isn't really a lot of knowledge in these models, unfortunately, at the moment. But I think what's interesting is that there's enough useful signal that we can actually make use of that, and that's actually what we've been doing. So Philip's got some really cool visualizations on his poster where he shows expert range maps, which are here in blue, and he shows outputs from commercial LLMs in terms of their ability to kind of generate range maps. And so you can talk to him, I guess, for more detail. But this kind of line of thinking spurred us to think about how we would go about incorporating additional context information into these models. So if you recall, we have this framework where we learn an encoder, and we have to learn some representation for each species. So we need a bunch of observation data for each species to learn this vector for it. But really what we're doing is we're just looking for some way to represent a species in the same d-dimensional space. So an obvious, or not obvious, but potentially obvious solution is to think about all this rich text data that's out there. Even going on Wikipedia, you can see pretty detailed descriptions of not just morphological attributes of species, but the kind of habitat preferences they have, the kind of range characteristics that they might embody. And this information isn't really encoded in the sparse observations we have in our training data. And so what we were motivated to think about is how do we actually incorporate such knowledge into the SDMs. And the simple way to think about it is we have some piece of text relevant to a species range. We pass it through some kind of frozen large language model. The kind of nuance here is that this is a text embedding model, not some kind of next token prediction model. So just a model that can summarize a piece of text into some feature space. We could have a small adapter here just to transform that into the space that we care about for our models. And so in a sense, in doing that, we have this ability to pass once trained, ability to pass a piece of arbitrary text into this model, and then we can use that to produce a predicted range according to our model for where that piece of text is likely to be relevant to. So, in a sense, all I've done is replaced the I've replaced the representation of species with a text encoder that can take an arbitrary piece of text as input. Okay, and we can train this model. So in practice, we train it on about 40,000 Wikipedia articles, just sections of text on it, and using the same type of iNaturalist data from before. Okay, so now this model is capable of doing things like zero-shot prediction. So once trained, we can take an arbitrary piece of text, put it into the model. So this is the example here. And so for species that are not present in our training data, we can actually we can make predictions. So you can see this example here. It talks about something found in Eastern Africa. And this is the kind of expert range here on the left, where yellow means where it's present. And this is the prediction from the model, which is not, not perfect, but not a million miles away. And what's interesting is kind of these, this model then has learned effectively how to map concepts into this spatial space. So we're effectively mapping the knowledge of this frozen large language model into a physical space. And so you can see here, this is where the model thinks locations that are relevant to India are, or tropical rainforests, or Great Lakes, and so on. You can also take totally out of distribution data. So if you want to know where your LLM thinks pasta is based, you can see it here. But we also have this interesting property where stuff that is highly unlikely to be described in our species range text is actually mapped as well. So for example, we have Hello Kitty here, or Simone Bolivar. So these are concepts that are not in the range text, but you can see the kind of power of these large language models. They've learned this kind of representation of entities, and maybe Hello Kitty matches to Japan, for example, and we have Japan probably described in our range data. So we have this kind of sharing of information across diverse concepts and topics. Okay, so we can then evaluate this model, and what we're interested in kind of at the moment is thinking about performance in this few shot setting. So this is where we have very limited observations for a species, so maybe on the order of like only tens. And we want to, again, on the vertical axis here, represent or characterize these performance for these species. And so in this case, this evaluation I'm going to show, it's for species that have not been seen by the model during training time. And so this is the original kind of model that I described, the basic signer model. What's worth pointing out here is, again, these species are not seen at training time. So the species embedding vector I talked about, we actually have to train that. And so in practice, what we do is we just train a logistic regressor where we add observations to the model. So we use the fixed location embedding, and then we train a logistic regressor to actually predict this. And we can see here with the model that's trained with the additional language information, not only do we get this ability to actually make predictions when we have zero observations, just by describing the range, what we also have is a superior performance in this low shot setting as well. So in some sense, that additional rich text information has provided us an ability to learn a better spatial representation, which we can then use to get better performance on this low shot setting. Okay, and so this is the kind of direction we're quite keen on in the moment, is to really think about how we can squeeze more performance out of this low shot setting. So this was our basic signer thing from the very start, learning species encodings explicitly. This is the language enhanced version that I just talked about, where we have to use text and then use that to learn a representation for species. The downside of this model is it doesn't have a native way to actually encode locations. It just can take text. It hasn't got a way to actually come up with a representation that uses the location information. So this kind of spurred us to think about maybe a more kind of general purpose way to doing both things. And the idea here, this is a paper that will appear at ICML this summer, is to have a more general purpose mechanism for encoding text information, images, but also location observations into a single encoder that can then spit out a representation for a species. So, for example, let's say we've got at inference time 3 observations for a species. We've also maybe got some text encoding. We can pass this into this transformer, which generates this species encoding, and then we use that in the exact same way as before to generate a map or prediction for this species. And what's quite nice about this framework is that it operates with variable number of input contexts or tokens. So I could give it 0 information as input, or I could give it one context or one location token, or I could give it just one text description, and this model is able to handle this kind of different input modalities and different quantities of them. Okay, and so comparing to before, I'm using different colors, but this was our Sinner model. This is the language one that we spent a few minutes talking about. And this is the model that is able to incorporate both locations, text, and then the nice thing about this approach is it doesn't require any additional training at inference time. I can just put that information into the model, and in a kind of a zero-shot feed-forward way, it produces an encoding for a new species. So while these approaches required me to kind of train an encoding for each number of location observations, here actually I can just do it in a single forward pass. Yeah, and so now we can do things like give it, for example, just a location as input. And so giving it just this location, this is the prediction from the model. But I can also do stuff like give it a location and a text description. And you can see how that modulates the predictions from the model. So if I say rainforest versus high altitude mountains, I get very different types of ranges predicted from it. So it's kind of giving or moving towards giving the user more kind of finer control over what kind of outputs these models could produce. Or for example, I could type desert as well, and you can see how the range is dramatically different, even though the location context is still the exact same. Yeah, and so here's a visualization as we increase the number of observations into the model. So if we give it one location here in North Africa, we give it another one here in South America, and so on. And so you can see the model kind of adjusting its predictions as it's given more data. So while there was no mass in some sense in Australia until we had this observation, as soon as we added it, we got this extra prediction. And again, I only alluded to it, but we can train these models also using visual data as well. So we use kind of species observation. So here's a prediction for a completely held out species. So this is again something that's found in the east coast of Australia, and we can see the model is predicting there and some other locations. Again, just seeing a photograph is a very weak piece of information, but you can see it's doing something plausible. And while I think this is not necessarily perfect, this is maybe like a best case scenario, we do observe this kind of generalization that we saw from the large language models as well, that we can put in images, for example, of this specific monument, and we're seeing a prediction here in Southeast Asia, which is reasonably plausible given this image. So again, this is not the type of image the model is trained on, but we can still pass it in and we'll get a prediction. Okay, so I want to kind of just wrap up and just kind of maybe allude to some of the limitations, and I think also think of those in terms of like the possible open questions that are left for, I think, a more AI audience for this problem space. So a huge one, which I've totally glossed over, are kind of challenges related to data biases and biases in the kind of observation process. So on the top here, we've got an estimate from another piece of work, not from my group, on terrestrial mammal richness. So darker red colors mean locations with more mammal species present. And you can see that there's a complete mismatch between those locations and where data is coming in on these citizen science platforms. So we have this huge bias to kind of global north and some other regions, but it's kind of like nearly the inverse in some ways of where the actual biodiversity richness is on Earth. And so this is a kind of an extreme spatial bias that's present. But there's also temporal biases. You know, there's certain times of day and certain times of year that people are much more likely to go out and collect data. And also there's huge imbalances. Now there's like very charismatic species that are really well represented on these platforms, and there's other things that are highly underrepresented. So I think there's a huge amount of insight we can gain from the kind of more statistical ecology literature on how we can improve those models, but there's a lot to be done there. We've also got evaluation. So this is, I think, in my mind, one of the biggest barriers to making progress from the AI side, because without kind of good gold standard metrics for evaluating performance, it's really kind of shooting in the dark in terms of how do we improve these models. And when you really get into the weeds and the nuances of it, it's a really hard problem to think about evaluation, because we just don't really have high quality range maps. And even when we do, I think it's like a pretty, in many ways, like really ill-defined problem when we get down to kind of very fine spatial scale. So thinking about evaluation for diverse taxonomic groups for globally distributed species is an important problem, but it needs a lot of work, I think, to move us forward. There's also questions around, finer grained ranges, and I suppose I also include some idea of like temporal predictions as well inside of this. This is a really cool example from Cornell Lab of Ornithology from their eBird project, and you have this kind of, not just this kind of higher resolution predictions, but you also have this characterization of range based on kind of, let's call it like behavior, in terms of like whether a bird species is present all year round, or it's just in the breeding season or non-breeding season. So they're giving this kind of extra insight into what's happening in this case. And I think moving again towards something richer like this would be really, really appealing. And another big problem is reinforcing errors. We don't want to be compounding errors that may be already present in these citizen science data sets and as a result of AI species ID and incorrect distribution maps, we've amplified this even further. So yes, there might be a panda in the zoo in Vienna, but it probably isn't a sensible observation to add into our range maps, because it's definitely going to be incorrect. In practice, this is kind of mitigated on these platforms because you're supposed to be uploading not domesticated or captive instances of species, but these things can still slip through. Okay, so takeaways. So I think the takeaway here is that we can actually estimate plausible species range maps from this highly noisy and biased citizen science data. And actually training, the big kind of thing that makes this work is training these models jointly on multiple species simultaneously really does help a lot. And this auxiliary information like text can provide a lot of additional value. And I think, again, it helps in the setting, which I think is the direction that we need to go more in. It's this kind of low shot setting. So people are uploading huge quantities of data to these platforms, but it's still, we're getting lots of the same. We're getting lots of pictures of ducks, and I think we don't need any more pictures of ducks. We need this kind of like long tail of species of things that are highly underrepresented, and that's hopefully going to improve over time, but it's still always going to be a long tail, and so we need to kind of target that tail in terms of improving these models. Yeah, and there's still many open challenges to be solved. I just alluded to some of them earlier on. Yeah, there's some references there, but these are kind of also on my webpage, which I'll have a link to on the last slide if anyone is interested. So yeah, big thanks to the team of people that worked on this. This is kind of led initially by Eli Cole and Chris Lang in my group, but there's a whole bunch of collaborators who've done a bunch of work on this as well. Yeah, and with that, I'm happy to take any remaining questions. Yeah.
Thank you for a great talk. I was wondering about mobility of species. Yeah, thank you. Hello? Okay, no, thank you. Perfect, yeah. I was wondering about, because your models seem to predict, like, for example, plants and animals, and I was wondering, the mobility of species, how does that, like birds can fly big areas, whereas a plant stays put?
Yeah.
So have you assessed that aspect of predictions?
Yeah, it's a great question. So, we have a range is not a static thing that stays the same all year round, certainly in the case of something like migratory species. I don't have slides for it here, but in the past we worked on temporal predictions as well. So it's actually quite simple. Like you have lat long, latitude, longitude, and you can just add in time of year. And with that, the model is able to then learn how to kind of encode these temporally varying observations. And so then we have this kind of ability to do things like move the slider in time and see predictions change over the year. This kind of does compound this issue related to how much data is available, and I think it does make it hard, because in many cases the model can start overfitting maybe seasonal patterns that it might think are present but are not present. So short answer is possible, long answer is that it requires more nuance and it's harder to evaluate. Yeah. I'll let you all decide how many questions I should take if there's a schedule. Oh, okay, we have time. Yeah, great.
Hi, thank you very much. So I was wondering, this is all kind of land-based species.
Yeah.
Is there hope to apply this to kind of ocean-based species, and is there data from boats, fisheries, etc.?
Yeah, a great question. I think we're going to hear more about marine species in the next talk. Short answer is, while I've a lot of the predictions I've shown, they've kind of masked out the ocean. There is actually a marine species in the data set, but it tends to be the case that it's on coastlines and so on where people observe stuff. So we don't have a lot of data, except for cruise ships. There's a lot of cruise-related observations happening. So short answer is, conceptually, it extends to that. Their data maybe on these platforms specifically doesn't support it. We are working with people at the moment who are doing things like trying to model plankton observations. And there are other repositories, I think OBIS is one of them, where there's kind of centralized efforts to bring together marine species. So yeah, I think it's definitely possible, and I'm sure will require more nuance as well.
Lovely.
Thank you.
Yeah, thank you for a great talk. I'm curious if you have any interesting qualitative insights about the results here. So, for example, if there's always a benefit to including this location prior, or are there scenarios where you actually perform worse when you include this type of information?
Yeah, it's a great question. I guess I'm assuming maybe you're referring a bit to the computer vision kind of use case, but I can also
exactly.
yeah, exactly. Okay, so where does it help? It really helps when you have two things that look very similar that appear in very different locations. That's kind of ideal setting. Where it starts getting problematic if you have two things that look very similar and appear in the same location, because now their range predictions are the same and their vision predictions are likely to be the same. And so then it starts getting problematic where you have maybe one thing that's much more prevalent than the other in that same location, because we likely will have higher confidence in that those locations that species is present. So there is a danger in those settings that more observed entities are kind of getting additional kind of amplification of their presence than rarer ones. So I think that's a case where it hurts. We've kind of looked at performance, in terms of the delta. Does it help or does it not? And I think on average, certainly it helps. And then there are a couple of these cases, like I mentioned, where it does hurt. And so I think there it's kind of nuanced. I think on these platforms you can do stuff like switch on and off the location prior, and so that allows you to kind of at least see how that would dramatically change the predictions of the model. So yeah, there are these cases where it hurts.
Yeah, thank you.
So in reference to the result that you showed, that the model performance improves as you increase observations and the number of species.
Yep.
But it's a scalar. Does it actually does it comes at the cost of less observed species?
Okay, good question. So in that evaluation, so basically what happens in our evaluation, we've got on the order of 2,500 species in the case of the plot I showed, or actually no, that was 500 species. And so each of them are evaluated independently. So this mean average precision, effectively what we do is we take the average precision between the prediction and the ground truth per species, and then we average them together. So what we're seeing then is the kind of overall average improvement. Does it actually hurt species, rare ones? I haven't looked into that explicitly, but my sense would be that it probably, we're seeing in general improvements overall, rather than actually being at the expense, because there's not really explicitly a trade-off in that setting.
Also, second question, in that setting, how do you choose the metric to evaluate when there is so much bias?
Yeah, I mean, it's a great question. So the kind of underlying assumption here is that the expert-derived range maps that we use are not systematically biased. That is a big assumption, but those are maps that are kind of curated by IUCN. They're used for their kind of red list assessment and so on. And then we have an extra filtering step where we remove range maps that significantly differ from the observation data that appears on INATS, because sometimes those maps are slightly out of date, or there might be like shifts in distributions that are not characterizing them, so we just remove those from evaluation.
Hi, thanks for a great talk. I was considering, like, similarly to how you define or how you show the pandas in the Viennese Zoo, like, how did you define presence in order to kind of filter out, like, anthropogenically induced presence? Like, only one annotation indicates that there is presence. That would be one case. And then the other question was, did you consider inter-class relationships, like interspecies relationship, like symbiotic? Like, when there's this species, it's likely that there is also this other species. Like,
yeah, makes sense. Okay, first question. We're basically doing very little filtering of data. So I think there's a lot that could be done there. And we're taking the kind of easy approach by just saying, let's put all the data into the model and see what we can do. I think that there's a lot more that could be done to kind of account for some of these biases. The second question, interspecies relationships. Implicitly, the encoding means that things that are learned to be similar in this representation space have this kind of similarity in terms of their range similarities. I think there are all these interesting kind of interactions that might be known and might be in the literature that could be encoded. You could imagine mining that in the same way we use the language model. Maybe you could think about using that to kind of represent some species interaction affinities. The reason we haven't gone down that path yet, or maybe will not, is thinking about where would we systematically collect like that data at the scale of 50,000 species. We could probably find all these little pockets where, yes, this thing eats this thing, but there's probably a whole bunch of interactions that are not explicitly observed in the literature that we wouldn't want to actively discourage the model to find because they're not in the data. Yeah, but I think it's an interesting direction. That's it. Yeah.
With that, I think we have to thank you very much. So let's give another round of applause for. We have a small present for you.
So I'm around all day if people have additional questions as well.
So thank you, Oisin, again for an excellent keynote. I learned a lot. With that, we are going to dive into aquatic marine species. So literally dive in with Edmund.